Welcome to the RDR 4000 IntuVue Weather Radar training for the Gulfstream G650. I'm Steve Hammack out of the Flight Technical Services Group. This presentation is Honeywell proprietary information and is subject to export restrictions and intended for personal use only. In this presentation, we'll look at a quick system description, the heart of the system, the 3D volumetric buffer, and the operational modes that the 3D buffer provides. Some examples of what you'll see, an introduction to wind shear detection, and some in-service experience from other aircraft operating the RDR 4000 system. Now we'll take a quick look at the system components. The main components of the RDR 4000 radar system include the antenna drive assembly located behind the radome and the radar processor located in the EE bay. The antenna drive assembly consists of a 24-inch flat plate phased array antenna, the antenna drive, and a line replaceable transmitter receiver module. The antenna drive is an all-new design incorporating many improvements for reliability and accuracy. The design uses low RPM direct drive motors. These DC brushless motors have no contacting components, no motor bearings, no gears, and no rotary waveguide joints, making the drive extremely quiet and reliable. It's a balanced drive which reduces the torque needed to move the antenna, and these improvements allow the antenna to scan faster and with greater pointing accuracy. The transmitter receiver module is mounted in the base of the antenna drive. It's an X-band transmitter operating at 9.356 gigahertz and uses nonlinear frequency modulation for pulse compression and is hermetically sealed. The receiver processes all returns and converts them to an intermediate frequency, which is then transmitted to the radar processor over coax cables. The new RF design and pulse compression provide greater system sensitivity, detection, and performance, along with new features including predictive wind shear detection. The radar processor, mounted in the EE bay, provides all the processing, display generation, and interface to aircraft systems. It's a small, lightweight box with high-speed Ethernet data loading, enhanced built-in test capability, fault reporting by flight leg, and event recording for predictive wind shear. Since it's an all-solid-state design, it provides for better reliability, repeatability, and lower drift. It also includes several methods to get information in and out of the box, including a compact flash memory interface, a front panel LCD display, and Ethernet connection. The front panel LCD display allows for more detailed information by maintenance personnel. From the LCD interface, ground and flight faults can be viewed, part numbers and software revision levels can be viewed, fault history can be cleared, and aircraft interfaces can be observed. One of the unique features of the RDR 4000 system is the 3D volumetric buffer. Current systems provide only range and azimuth information, but the RDR 4000 system adds a third dimension, which is altitude. One of the first things you'll notice about the RDR 4000 system is that there is no tilt control. The system automatically and continuously scans and collects weather and ground returns from the nose of the aircraft out to 300 nautical miles and from the ground to 60,000 feet. For scans above the freezing level, the system automatically increases the gain to make less reflective frozen storm tops more visible. The scanned information is stored in a 3D volumetric buffer, or memory, and it is continuously updated and compensated for aircraft movement. The data is also corrected for the Earth's curvature, so that the altitudes that you get from the system are true MSL altitudes. If left uncorrected, the effect of the Earth's curvature can be quite significant. In the picture shown, the aircraft is at flight level 250, but because of the Earth's curvature, the center of the beam is above 27,000 feet at 60 nautical miles, almost 37,000 feet at 120 nautical miles, and at 44,000 feet at 150 nautical miles. The automatic scanning stores all of the weather and ground return information in the 3D buffer memory. The system also contains an internal worldwide terrain database that is a version of our EGPWS database, but without airports, runways, and obstacles. Because the RDR 4000 uses only the terrain information, regularly scheduled updates are not required. The terrain database allows us to distinguish between weather returns and ground returns. This allows us to show only weather information in the weather modes and only ground returns in the map mode. In radar map mode, the ground returns are provided by the radar returns and not the internal terrain database. This allows for an independent verification of position. Other information that is put in the 3D volumetric buffer includes enhanced turbulence data. Turbulence detection is automatic and is provided out to 40 nautical miles for any range selection if enabled. The RDR 4000 system is the first system certified to the FAA's new Enhanced Turbulence Minimum Operational Performance Standard, or MOPS. It provides more sensitive and accurate turbulence information with fewer false alerts and improved correlation to predicted aircraft G-forces. It is up to 12 times more sensitive than current systems and is displayed plus or minus 5,000 feet around the aircraft altitude. You can think of the 3D volumetric buffer as a giant Rubik's Cube. Each square is at a certain position in range, azimuth, latitude, longitude, and altitude. In each of these squares, information is stored about reflectivity, turbulence, and if the returns are weather or ground. Since there is no tilt control, you're not using the control panel to control the radar, but rather you're using it to request information from the 3D buffer. This information can be presented in many ways, including comparing the weather in the buffer to the aircraft's flight path or vertical flight plan, and showing the weather on the flight path in solid colors, as shown here, and weather outside of the flight path in a different pattern, as shown here. We can also extract vertical views of the weather from the buffer and present it on the vertical situation display, or VSD. Because of the beam width resolution, weather on the VSD is limited to 100 nautical miles. We can do this along the aircraft's track, as shown here, or along a manually selected azimuth, as shown here. In this picture, we've also selected a constant altitude slice at 37,000 feet. We'll talk about manual altitude slices in just a second. Also, it can be shown along the aircraft's lateral flight plan on the VSD as if it were a straight path, as shown here. We can also extract Earth curvature corrected constant altitude slices out of the buffer and present them. Here we see the same storm cells with slices at 14,000 feet and 27,000 feet. This analysis mode provides a simple means for making deviation decisions. So now that you know what can be done with the 3D volumetric buffer, let's look at the modes on the G650. I always like to break weather usage into detection, analysis, and avoidance. And the RDR 4000 provides you with modes for detection and analysis, letting you concentrate on avoidance. Strategic detection is provided in the WEX Auto mode and on the vertical situation display. Analysis can be done using the WEX Man mode and using the vertical situation display. The system provides turbulence and wind shear detection as well. Standby mode is the default power-up mode. When standby mode is selected, the radar is not transmitting and the antenna is not scanning. The RDR 4000 system uses a solid-state transmitter that does not require warm-up time. Forced standby mode inhibits the radar from transmitting on the ground. It is set when on the ground and the selected mode is WEX or ground mapped. Forced standby mode can be overridden using the control panel and is automatically deselected when the aircraft transitions to in-air, and the mode will then change to the last selected mode. Ground override is automatically deselected when in the air, when both SMCs have failed, or when manually deselected. When it is safe to transmit, override should be used so the 3D volumetric buffer can begin to fill with data. In test mode, the system will run a complete system test, checking each of the system components and aircraft interfaces. When the actual test is running, the test annunciation will flash in green. Test will stop flashing once the test is completed. If ground override is selected, the test pattern will continue to be displayed. Otherwise, the test pattern will be removed at the completion of the test sequence. If the predictive wind shear option is installed, the wind shear icon will be overlaid on the iNav map and on the HSI. Check for the proper appearance of the test pattern, oral callouts, and wind shear icon on the display. The predictive wind shear caution and warning enunciations will appear on the ADI during test. If the predictive wind shear function is not available or not installed, it will be enunciated in the CAS window during test mode and normal operation. When test mode is initiated, the test pattern will appear and the system components will run an initiated test that can take up to 12 seconds to complete. After that, the pred wind shear will appear in amber on the ADI with the associated caution wind shear ahead audio. After that, the pred wind shear will appear in red on the ADI with the associated warning wind shear ahead audio. If the predictive wind shear option is not installed, the test pattern will look the same with the obvious exception of the wind shear icon, the enunciations on the ADI, and the oral callouts. It's a good time to talk about radar safe. FAA Advisory Circular AC 20-68B defines the safe distances when operating radar systems. Manufacturers must calculate two distances. The first is where the radiation level exceeds 10 milliwatts per square centimeter, and that is 7.55 feet or 2.3 meters in front of the antenna. The second is the near field far field boundary, which is a fancy term for how far ahead of the antenna the beam actually forms. That distance is 11 feet or 3.35 meters. So we take the larger of the two, and that defines the safe distance. In test mode, we transmit a very short pulse, and the safe distance in test mode is 0.51 inches or 1.3 centimeters in front of the antenna, so it doesn't even make it out of the radome. The last item of interest is the safe fuel distance, which is 2.24 feet or 68.3 centimeters. Now we'll take a look at the different modes, starting with the WEX Auto mode. This is done by selecting the mode to WEX and altitude select to Auto. This is the mode that you'll be in the majority of the time. Turbulence and wind shear detection should also be selected on. In WEX Auto mode, the system analyzes the data in the 3D volumetric buffer and compares it to the aircraft's vertical flight plan or the actual flight path if you're not following your vertical flight plan. It then shows the weather in the flight path in a solid pattern and weather away from the flight path in a hashed pattern. During this presentation, I will use some terms interchangeably. Flight path weather is also referred to as primary weather, and secondary weather is weather off the flight path. I will use vertical flight plan and flight path interchangeably as well. The concept of separating the weather into primary and secondary is the same regardless of the source of your vertical path. Let's look at a couple of examples. In the first one, the aircraft is straight and level below 25,000 feet. Both storm cells are a threat based on the flight path, and the display would look like a normal radar display with both cells displayed in solid colors. The normal envelope around the flight path is plus minus 4,000 feet for weather. Turbulence information is displayed plus minus 5,000 feet around the aircraft altitude if selected on. Now we begin our climb up to cruise altitude. The cell closer to the aircraft is in the flight path envelope and is still shown in solid colors, but the second cell is way below our flight path and will be shown, but in a hash pattern indicating it is outside of the flight path. Flight path is determined by using vertical rate and ground speed and is extrapolated out to 60 nautical miles because we don't assume you will climb or descend forever. At 60 nautical miles, that altitude is used as the altitude for beyond 60 nautical miles. If the vertical flight plan is available and is being followed, the system will use the flight plan altitudes. In this example, we are at cruise but beginning our descent. Based on our flight path, the second cell will now change from the hash pattern to the solid pattern, indicating that it is on our flight path. The normal envelope around the aircraft is plus minus 4,000 feet. However, when you pass through 25,000 feet, the bottom of the envelope becomes fixed at 25,000 feet and goes to 4,000 feet above your altitude. Most inadvertent turbulence encounters, especially at night, are due to less reflective frozen storm tops, which are not reflective to the radar. The RDR 4000 system does several things to make these cells more visible. First, in the collection process, the gain is increased when scanning at higher altitudes. Second, the flight path envelope never goes higher than 25,000 feet. And third, what is shown is the maximum reflectivity at any point from 25,000 feet to 4,000 feet above your altitude. Here's an example of a typical storm cell. If you look at the solid lines, they represent isoecho contours or lines of constant reflectivity. Up at the top of the cell, the reflectivity is only 20 dBz, and that would normally be shown as light green on the display. If you look at the arrows in the picture, they represent the wind speed and direction in the cell. At the bottom, you have inflow into the cell, but look up at the top. These arrows are the longest, indicating that they have the strongest updraft velocities, but all you would see is light green on the display. Here's what it would look like on a legacy radar system. Close to the cell, the beam is very narrow and intersects the cell at high altitude where the frozen particles are less reflective. Although this cell had enough energy to lift moisture over 37,000 feet in the atmosphere, it would only show up as light green on the display. So for any given point on the display, the RDR 4000 looks into the buffer from 25,000 feet to 4,000 feet above your altitude and extracts the maximum reflectivity for each point on the display. This is like a 3D CAT scan or MRI of the storm cell, but in this case we call MRI maximum reflectivity indication. So in the case of this cell, instead of just showing light green on the display, we would show green, yellow, and red, alerting you of the hazardous condition. This is a more graphical representation of the WEX auto mode. The translucent wedge indicates plus or minus 4,000 foot envelope around the aircraft. Here we are flying straight and level, and where the wedge intersects the cell in front of us, it is shown as a solid pattern. The low-lying weather off to the left is still shown, but is shown in a crosshatch pattern instead. This table is shown in the pilot's guide and looks somewhat daunting, but it's really pretty simple. The normal flight path envelope is plus or minus 4,000 feet around the aircraft's flight path. As we described, the bottom of the envelope never goes above 25,000 feet so that frozen storm tops are more visible. So when you reach 29,000 feet, which is 25,000 plus the 4,000 foot envelope, the bottom of the envelope stops at 25,000 feet. Likewise, on takeoff, approach, and landing, the top of the buffer never goes below 10,000 feet, which is 6,000 plus your 4,000 foot envelope. This gives you about 10 minutes look ahead into your flight path. In the WEX auto mode, the VSD will show a vertical view of the weather along your lateral flight plan as if it were a straight path. If the flight plan is not defined or the aircraft is not following the flight plan, the VSD will display weather along the aircraft's track, and this will be enunciated at the bottom of the VSD. If the VSD manual mode is selected, then the azimuth slices can be selected from plus and minus 180 degrees for viewing and analysis. The selected azimuth is set using the range set knob, and a gray line will appear on the map indicating the selected azimuth. A digital readout of the selected azimuth will be shown below the VSD display. When the altitude select is set to manual mode, constant altitude slices can be displayed from the 3D buffer. The selected altitude slice is displayed below the mode, and a gray line is shown on the VSD indicating your altitude slice. This mode allows you to select horizontal slices from the buffer that are corrected for the Earth's curvature so that they are true MSL altitudes. The captain and first officer can have different altitude slices selected. The initial slice will be at the current aircraft altitude and then can be dialed up or down from 0 to 60,000 feet in 1,000 foot increments. The selected altitude is maintained regardless if the aircraft is climbing or descending. For altitudes below ground level, nothing is shown on the display. Turbulence information, if selected for display, is shown for the first 40 nautical miles on any range selection. It is shown for plus or minus 5,000 feet around the aircraft altitude, but is not shown on the VSD display. If selected, the mode is displayed as WEX/T. Now let's go over a few simple examples to make sure you understand the different modes and displays. In this example, we're in WEX auto mode and flying straight and level at 20,000 feet. We have weather from 60 to 80 nautical miles ahead of us. So what would it look like on the display? The first thing to remember is the envelope is plus or minus 4,000 feet around the aircraft, or from 24,000 feet to 16,000 feet. Since this is outside of our flight path envelope, the weather is shown in a crosshatch pattern. Now let's go to the WEX man mode and look at an altitude slice. Remember that when we enter WEX man mode, the initial slice is at the current aircraft altitude, or 20,000 feet in this example. So what would we see on the display? Nothing, because the weather is above the selected altitude slice. The easy way to think about this is that in the WEX auto mode, you see all of the weather. It is just separated into flight path or secondary weather with the solid pattern of the hatches. In the WEX man mode, you only see the weather at the altitude slice that you have selected. Now let's dial the altitude slice up to 39,000 feet. What would we see? We'd see the weather up above us. Let's look at WEX auto mode again, but this time we're at flight level 390. Remember, the bottom of our envelope never goes above 25,000 feet and goes to 4,000 feet above the aircraft altitude. So it goes from 25,000 feet to 43,000 feet in this case. So what would we see? We would see solid green from 60 to 80 nautical mile range because it's in our flight path. I purposely drew the red smaller than the green to illustrate a point. The flight path weather always has priority over the secondary weather. Remember, this system is giving you altitude information. It's telling you that there is weather above 25,000 feet. So always think about altitude first and then color. Now we're at the same altitude, but I've changed the picture slightly. So what would this look like on the display? From 68 nautical miles, it would look the same, but where the secondary weather isn't being covered by the primary flight path weather is shown, but in a crosshatch pattern. So now we have the same weather, but we've reached our top of descent point and we're starting down. What would the picture look like now? Since we're now descending, our flight path changes, and so will the picture. The red is now in our flight path and covers up the green, which is secondary to our flight path. It isn't necessary to memorize the altitudes the system is using as long as you have a basic understanding about what the system is doing and showing you. If you're ever in doubt about what the system is showing you, use the WEX man mode to look at altitude slices and build up your own mental picture of the weather. Now we'll talk about gain control and its use. Most of the time you'll be in the auto or calibrated gain position. Taking it out of the auto position allows you to select -16 to +10 dB of gain. Using gain is really quite simple. If you look at a model of a storm cell, it's not as reflective of altitudes above the freezing level and very reflective around the freezing level and below. So the gain knob is like a volume control in your TV or stereo. If the music is loud or very reflective, then you would only want to turn it down. If the music is very soft or less reflective, then you want to turn it up. So to put it in more radar terms, some of the uses for gain are, if you reduce the gain to minimum, what's left are the strongest cells and turbulence. Gain doesn't affect turbulence detection, so any cells remaining, and especially those containing turbulence, should be avoided. Reducing gain in heavy stratus rain can also help you identify embedded cells by looking for radar shadows. Increased gain is useful when you're looking at frozen storm tops and should be used in the WEX man mode when you are measuring the tops of cells. Remember to turn the gain to auto once you have completed your analysis. With a normal pencil beam antenna, you would just get a narrow swath of ground returns. The RDR 4000 pieces all of these narrow swaths together to give you an extended ground map. Map mode is useful for identifying prominent features like coastlines and lakes. The ground returns are actual radar reflectivity and not from the internal terrain database. This gives you an independent verification of position. In map mode, weather returns are not shown on the VSD display. This picture shows a satellite view of the Puget Sound area and the radar ground map. Ground map is optimized for longer ranges and weather returns are suppressed. However, over areas with very low reflectivity like water, some weather returns may appear. Ground map mode can also be used to identify areas of attenuation. The two pictures shown are from the same area. The picture on the left is weather with the ground returns suppressed. The weather on the right shows a ground map with the weather suppressed. You can see areas where ground returns cannot be seen, indicating attenuation or radar shadowing. The weather here is strong enough that the radar beam cannot penetrate any further, so the storm may be worse than it looks or may extend further than it appears. The power-up defaults are shown here. The selected mode is standby, VSD weather is selected on, turbulence is selected on, predictive wind shear is on if installed, otherwise it's not shown or selectable. VSD azimuth is set to auto, the altitude select is set to auto, the gain is set to auto, and the ground override is set to off. The display enunciations are as follows. The mode can be forced standby, standby, test, WEX, weather turbulence, or fail. The next line, forced override, is shown or blank. The next line, the selected azimuth angle, slave or blank. And the next line, the selected altitude slice or blank. Slave is displayed in amber on the on-side display if the on-side SMC has failed. This enunciation indicates that the on-side weather radar controller is a slave to the other side. Any on-side selections, except for the range control, made on the off-side SMC affects the on-side display when in this mode. The slave mode is deactivated when the affected SMC is operating normally again. The mode enunciations are green if WEX is selected for display and amber if WEX is not selected for display. Test will flash while the test is running. Force standby, override, slave, and fail will all appear in amber. We've described the full functionality of the RDR 4000 system in this tutorial. In the initial certification, the vertical display of weather is disabled, and the WEX auto mode will always use the aircraft's flight path for the envelope and not the vertical flight plan. Since both modes look and act similarly and the flight path mode is the backup for flight plan mode, we describe them both in this tutorial. Both features will be included in the next block point upgrade. Since the Gulfstream G650 is the first business jet to have predictive wind shear detection, we'll spend a few minutes explaining this function. Predictive wind shear has become the industry term, but unfortunately is somewhat misleading. There are many types of wind shear, but what we are concerned about is a specific type called a microburst, and there's nothing predictive about it. The radar actually measures the speed of the raindrops to detect microbursts ahead of the aircraft, so a better term is forward-looking wind shear detection. A microburst is a vertical cylindrical shaft of rain-cooled air. The air in the upper part of the cell is cooled by supercooled water droplets. This colder air is heavier and denser than the underlying warm air, and at a point in the storm, this heavier air breaks loose and rushes to the ground at hundreds of feet per minute. Upon reaching the ground, the air mushrooms out in a radial direction. This picture shows a typical wet microburst, and this picture shows a dry microburst typical in arid areas like Denver, Colorado, and Phoenix. They can be relatively devoid of moisture and appear like Virgo, where the rain evaporates before reaching the ground. To an aircraft on approach for landing, the aircraft would first encounter a headwind and increase lift. The pilot's natural tendency would be to reduce pitch and possibly power to remain on the glide slope. Next, the aircraft would encounter the downdraft in the center of the cell. This air is descending at hundreds of feet per minute, and the aircraft is in that air mass. As you exit the downdraft, you encounter a tailwind and additional loss of lift. All of this is when you are low and slow, power reduced, and in a dirty configuration. The radar looks ahead of the aircraft and measures the speed of the raindrops. Those coming toward the aircraft appear to be moving faster, and those moving away appear to be moving slower. The radar looks for this fast to slow profile over a certain distance and provides wind shear alerts. If you compare this to a reactive wind shear system, the difference is in the advanced warning that the predictive wind shear system provides. Reactive systems use accelerometers and aircraft inputs like airspeed, ground speed, and altitude to detect that you're in a wind shear. NASA studies have shown that as little as 10 seconds advance warning can significantly improve your chances of recovery. Warning times for wet microbursts are significantly longer and allow time to increase the aircraft's energy state by allowing the engines to spool up and to get the aircraft cleaned up. The systems are very complementary, with the predictive system giving advance warnings and reactive systems providing alerts for wind shears without enough reflectivity for the radar to detect. With wind shear detection selected on, the process is automatic. Qualifiers automatically activate wind shear scanning and detection. On the ground, the qualifiers are ground speed greater than 25 knots to activate and less than 15 knots to deactivate, and left or right EPR greater than 1.25 to activate and less than 1.2 to deactivate. Cautions and warnings are based on the proximity of the wind shear, azimuth, and range. Warnings are given for wind shears within plus minus a half a nautical mile of the aircraft's heading and out to 1.5 nautical miles. Cautions are given for wind shears within plus minus 25 degrees and 1.5 nautical miles. After takeoff, alerts are inhibited until above 50 feet AGL. On descent and landing, wind shear activation occurs when descending through 1,800 feet AGL so that alerts can be given below 1,200 feet AGL. Warnings are given for wind shears within plus or minus a half nautical mile of the aircraft's heading and out to 1.5 nautical miles. Cautions are given for wind shears within plus minus 25 degrees, 3 nautical miles. Below 370 feet AGL, the warning range starts to decrease so that the system will not generate a wind shear warning beyond the touchdown zone, and then you do a missed approach and fly into it. Alerts are inhibited below 50 feet AGL and 60 knots. When a wind shear is detected, an icon will appear on the display indicating the range and azimuth to the event. Flashlight beams appear as yellow lines on both sides of the icon and extend from the icon to the outer edge of the display for all range selections. This makes the azimuth apparent even with a long range selection. A red pred wind shear warning or amber pred wind shear caution will appear on the ADI, and the corresponding audio call out of warning wind shear ahead or caution wind shear ahead will be heard. The RDR 4000 also has the capability to record wind shear events for analysis. Up to 32 events are recorded, including the time, location, and severity. For the 5 most recent events, the actual raw radar returns are also recorded. Now that we've looked at the system in detail, let's take a quick look at some in-service experience on other aircraft operating the RDR 4000 system. This system is much easier to use than traditional radar systems, but it is different, and you just need to understand those differences. And the key is to always think about altitude and not color, or better yet, think about altitude first and then color. The third dimension that the radar gives you is altitude, and all the modes use this altitude information in some way. Why do we even look at color in the first place? If you look at the two charts shown here, you can see that as reflectivity increases, so does the probability of turbulence and hail size. For example, at 40 dBz, which is the beginning of the red color, there's a 40% chance of moderate turbulence and a 5% chance of severe turbulence. But I always say that the probability in statistics is the science of proving nothing. A 40% chance of turbulence means there is a 60% chance that there isn't. And the chart is for convective weather. So you first need to determine that it's convective weather to apply. But with this cell, I can give you a 100% probability that you encounter turbulence. This is what you need to be able to use a weather radar to do, to detect convective activity or weather with vertical development. And the only way to do this is to look at the height or altitude of the cell, our third dimension. Unfortunately, over the years, many pilots have been taught to avoid red cells only. But you can be flying in areas of heavy stratus rain, like in South Florida, that have nice big reflective raindrops and paint red or yellow on the display, but it is fine to fly through because it's a stable atmosphere. I showed you earlier the light green on the display at cruise altitudes due to the less reflective storm tops that are very dangerous to fly through. So in one case, I have a good red, in the other case, I have a bad green. So what's the difference? The difference is that one is convective and one is not. So looking at the vertical development of a cell is very important, and the RDR 4000 gives you the tools that you need to do that. One of the things that pilots observed when they first started using the new system is that they were seeing magenta turbulence indication in black areas. If you look at the reflectivity chart shown in the picture, you can see that black doesn't mean that it's not raining. It's just raining at the rate below the threshold the FAA has set for green, which is 20 dBz. With older radars, to detect turbulence below the green threshold, you would have needed to be about 3 nautical miles away to see turbulence in black reflectivity. But because the RDR 4000 is much more sensitive, it can detect turbulence at the same level at about 15 nautical miles. The turbulence detection capability on this radar is much more sensitive and accurate, so keep it turned on and learn to trust it. Although we've made many improvements to the radar, there are some physical limitations that can't be overcome, and beam width resolution is one of those. At long ranges, the beam is so large that you don't have good resolution. That's why the VSD display is limited to 100 nautical miles. Because of the beam width at long ranges, all weather will appear as flight path weather, and as you get closer, it will separate into primary and secondary weather. This isn't a problem because you normally wouldn't be making deviation decisions that far out. Another thing pilots mention is that the systems seem to be oversensitive, showing targets stronger than they were used to. Here we use our key. The reason is because we're looking down to 25,000 feet in the buffer, showing you the more reflective part of the cell. But again, think about altitude first and not color. What the system is telling you is that this cell is over 25,000 feet. It doesn't matter what color it is. This cell had enough energy to push moisture over 39,000 feet into the atmosphere, and it's hazardous. And here's an interesting one. Cells appear less sensitive. I just said they said they were more sensitive. Well, some said they were less sensitive. In this one, what I've done is I've decreased the height of the cell. But remember that the primary flight path weather always has priority or covers the secondary weather. So in this case, the green covers the yellow and red at the lower altitude. But again, use the key. Think about altitude first, then color. The system is telling you that this cell is moisture above 25,000 feet. We talked about the envelope around the aircraft and how the bottom of the floor never goes above 25,000 feet. In some parts of the world, you can encounter high stratus layers that will sometimes exceed 25,000 feet. Since it's above the 25,000 foot floor of the envelope, you could have large areas of green, yellow, or red on the display shown in solid colors. The stratus can be fine to fly through, but it makes it more difficult to see embedded cells within the stratus. An easy way to handle this is to have one side in the WEX auto mode and the other side in the WEX manual mode. In the WEX manual mode, you can dial the altitude slice up above the stratus layer and see any embedded cells within the stratus. So here we have the stratus layer, and the yellow line represents an altitude slice above the layer where the embedded cell is visible. Just a few final thoughts on differences. You're going to see more weather, and that's a good thing. You'll see weather at longer ranges because of the higher sensitivity. You'll see weather closer to the aircraft because of the 3D buffer and all the different tilt angles that we use, both up and down. And you're now looking at weather horizontally as opposed to just the single diagonal slice that you used to when you use tilt. When you turn the radar on, the 3D buffer will begin to fill, and it'll continue to provide more and better information for about 29 seconds until it completely fills. This is normal. You're going to be in the WEX auto mode most of the time, and for isolated cells, you can do all your weather detection and analysis in this mode. Use the WEX band mode and the altitude slices for analysis and deviation decisions when it isn't clear in the WEX auto mode, or any time you don't understand what auto mode is showing you. And always remember, think about altitude first. Something that'll look a little bit different because of the 3D buffer and the motion compensation is interference patterns. This picture shows a typical interference pattern usually caused by military radars. They can be from fighter aircraft, ground-based military radars, and I've also seen them from radars like the Port of Seattle. They can appear as red, yellow, or green spokes on the display of a legacy radar. On the RDR 4000, they look a little bit different because they're collected over multiple sweeps, motion compensated in the buffer, and separated into primary and secondary returns. They look similar, but not exactly the same, so we just wanted you to know what they look like. We'll finish up talking about avoidance. Most pilot's guides that I've seen over the years have suggestions like these. Avoid any cells containing yellow, red, or turbulence indications by at least 20 nautical miles. For cells exceeding 28,000 feet, it doesn't matter what color they are, avoid them by 20 nautical miles. And cells exceeding 35,000 feet should be considered extremely dangerous and should be given additional separation in addition to the 20 nautical miles. Unfortunately, most pilots didn't have the ability to easily determine the height of a storm cell, but with the RDR 4000, we've given you the tools so you can make proper avoidance decisions. And thank you for joining us today.